So in this lesson, I'm going to take you through another example of using the Essential Rainwater Harvesting tool to size a system. This time we're going to look at an off-grid system and some of the different ways we might approach the optimization of that tank sizing. And also in this example, I'm going to use the version 2.0 beta of the tool and compare back to back the monthly results from the daily results. And it'll really highlight the differences in outcomes that can be achieved depending on how you think about it. So with that, let me start by opening up, and as always, file save as. I'm gonna name this Oregon off-grid. Okay, let's zoom in a little bit now so that we can see and go through these cells together. Project name, of course, you can put whatever you'd like here. This is really just gets copied onto the summary tab. Example. I'm going to skip over a few of these things. Time step in the beta version now you can't select daily anymore because the daily is managed all on this daily tab. And this time let's do it in US customary, given that I'm going to be doing an example in Portland, Oregon. Country, US, state, OR, and then the dataset location. Just for the, again, for the example here, let's compare the climate normals data that's already populated inside of the Essential Rainwater Harvesting tool, and we'll compare that to the daily data. You could also, of course, input your own climate normals by selecting this. Moving on to part 1. So we can see that, scroll over here, we're at the beginning. We're going to start by collecting the data, and we're going to start with the supply. The rainfall data has been populated into the tool for the monthly time step. Scrolling over. You know, it is a really good idea to collect this data. For this example, I'm going to skip over it. Now, average supply. We are going to use a roof efficiency of 0.98. Our scenario is that we have an off-grid home. The owners are building it off-grid, and they know already that they want to be off-grid. They're very close to Portland, Oregon, so that's the weather station we're going to use. They already have their house designed out and are just trying to wrap their head around how big of a tank and whether or not they can go fully rainwater supply, or whether or not they have to look at other water supply options. Because they're going to do a really good job with installing their roof, we're going to just use a roof efficiency of 0.98. And the area they have for their harvesting surfaces, I'm going to put 3,000 square feet. So yes, it's quite a large area, but you know, because they're off-grid, they've got you know, presumably maybe a couple sheds and a roof collecting water for themselves. So the moment I put this in, the tool is now calculating their average supply, their supply annually, and a supply on a monthly basis. Moving along, step 1.3 is the total indoor water demands. Calculate the total water demands for your home, including even the non-rainwater uses. So we know these this family is hoping to have 100% of their indoor water supplied with rainwater. So their total indoor water demand, gallons per month. I'm going to open up a spreadsheet. What this family has gone and done is that they've actually been measuring their household water use for the last 12 months, or preferably even longer. And they've produced this little graph, this little chart that shows how much water they used in each month in gallons. And just for visual purposes, they've plotted it out so you can see that this is what they're using. So they've done a really good job actually getting actual water demands, which is great. It's ideal. From here, we need to put these water demands into the spreadsheet. So I'm going to show you a little trick. Let's do this, and then let me just shrink this guy down so that you can see both spreadsheets. They've got a total indoor water demand, and there's only the opportunity here to put one number. I'm going to have to do a little bit of math. This is what I'm going to do. There's a couple different ways you can do this, guys, but just I'm going to use some Excel logic, figure out what my minimum, this is my smallest month. I just use this min function, and then I'm going to divide each month here by my minimum month. If you don't know much about Excel, basically I'm using these dollar symbols to create an absolute reference, meaning that when I drag this equation down, this cell never changes. What I've gone and done here is simply, there we go, come up with some factors for each month related to the smallest month. So what that allows me to do is in my tool, oops, right, we're going to say 100% of their indoor rainwater demand is the total indoor rainwater demand. And you can see as I inputted method A, method B disappeared. Outdoor rainwater demand is 0. We're not going to use that. They're purely interested in their indoor water demand at this point. And here's where these factors become useful for me trying to get this varying month by month water use into this tool. I can use these indoor demand factors to come up with the same profile. 1.1. And so by setting the total indoor water demand to my minimum and just doing a little bit of math, I'm able to come up with factors that essentially create the same demand curve. So that's something you can do. Plan to irrigate, it's set at yes, 100%, which I'm going to leave it as is because the outdoor rainwater demand is 0. I could also just go ahead and set those to no's. It would come up to the same result. And then if we scroll down here, you'll see that the demands on the monthly time step per month on a monthly basis are the same as what I have in this spreadsheet. Supply to demand ratio. In this particular climate, they get lots of rain, so this is looking really good so far. The annualized supply to demand ratio is 3.13. We can go on to part 2. Now we're on part 2, where we actually are going to attempt to optimize the storage based on the monthly average inputs. The tab automatically pulls my catchment area from part 1, and this is the storage capacity that I will start iterating and guessing at to try and understand the performance happening in these columns here. I'm just going to take a stab and throw in a 1,000-gallon tank. Commission month, we're not going to be too fussy about this. You could put if you knew what it was. The minimum stored volume, for now, or just leave that at 0, and the initial tank charge, again, I'm going to leave that at 0 as well. So what we're seeing in this optimize your storage on the monthly basis is that with a 1,000-gallon tank, the tank is going to run nearly dry in July and completely dry in August, which is actually pretty impressive. That's not a very big tank. It really does go to show that I picked an area with a lot of rain. You wouldn't have anywhere near this result if you were somewhere a much drier climate like where I'm from in Alberta. Regardless, that's not acceptable, so we're going to go higher. We're going to try a 2,000-gallon tank. And there we go. We have better performance, and both July doesn't run dry and August doesn't run dry. Same with September. So the owners might stop here and say, okay, well, it looks like a 2,000 gallon tank is going to work. But the thing they have to remember is that this is based on average rainfall. We've only really modeled the performance of their tank and their catchment and their demands based on one calendar year using average inputs. So even though they're satisfied with the average inputs, we need to go to part 3 and stress test and redesign for low rainfall. So what happens when we don't get average rain in a year, which we all know is going to happen? So in part 3 of the model, they now have to make some decisions about what kind of rain reduction due to drought is reasonable. Let me just scroll this back up again. What kind of reduction due to drought is reasonable? You might, if you lived in this climate, you might have a pretty good idea in terms of how variable the climate is. You might not, but the easiest thing you can do is just to start play around with it. I'm going to put 30 for the month of January, and I'm going to use an equation just to quickly be able to change that for all these months. Let's try 30. So 30, looks like I need to input my drought commencement month before this table will populate. All right, here's my storage performance in the drought years. So in a 30% reduction in rain, there you go, August and September, the tank is dry. And that's probably not acceptable for an off-grid tank scenario. Let's see what happens in 40%, and let's see what happens in a 50% reduction in rain. My suspicion is that if you were truly in an off-grid scenario, you'd want to be testing the rain reduction in a 50% reduction of rain. But again, it's pretty context specific, and you just have to think about what makes sense for your particular scenario. Let's start increasing our storage capacity to see which storage volume we get. There's 3,000. There's 4,000. So at 4,000, at a 4,000 gallon tank is when in August and September we're finally not getting zero tank volumes in our tank anymore. And you can see that by left, there's just a little bit of 50 gallons left in the tank at the end of September with a 4,000 gallon tank. I think if I was designing this off-grid rainwater system for this family, if they were willing to possibly cut back on their rainwater uses in September and August, I say August and September, right? Those are the months where they could gain a lot more confidence that they wouldn't hit rock bottom. And as Peter and I have discussed, that it is absolutely true that rainwater system users do adjust their demands based on the level in their tank. It is feedback that happens. So using the monthly model, I've come up with a storage capacity, an ideal storage capacity of about 4,000 gallons. Let's go yes. And the summary table here will summarize those results for me. Right, there's my 4,000 gallon tank. Now I want to show you guys how to test that assumption with the daily. The monthly model works really well in that the data is easy to get, and Excel is not cumbersome. What I think you're going to find, and I'll try and show you in this example, is then when we start getting the daily data, it can be a little bit, Excel can be a little bit buggy. Let me show you what I mean. We're now at the daily tab. We've already completed the start tab and steps 1.3, 1.4, 1.5, and 1.6. So the demand volumes have been populated in here. You can see the gallons per day is about 50 gallons per day indoor rainwater demand. It varies a little bit, but about that. Let's go get our daily data. Search tool, daily summaries, Data set range, we're gonna do December 31st of 2019, and then we're gonna go back 30 years. So 2009, 1999, 1989, January 1st. Apply. There's my 30 years of data. Search for. In the US, I found it works quite well to search for cities. We'll see. We might go back and search for stations, but let's try. Portland. Let's try Portland Airport. This isn't quite the right station. Let me do more search options. Stations. Search. There you can see there's more stations that have shown up here. Here's the International Airport. This is the one I want. And if I click on it, it shows you where the station is, gives you some data coverage. I do like airports. I find that they have excellent data coverage. So if it makes sense to use an airport, go ahead and do that. This is just the information about that data set. Oh, here we go. Add to cart. This is the button I want. So it's been added. And then once you view your items in the cart, again, we want the CSV file. The date range is the one I initially suggested. Continue. Let's do standard units this time. Let's get precipitation and air temperature. Continue. Submit my order. Here's the file that I've just downloaded from the Climate Data Online website. Zoom in a tad here. There's a little bit more. You can see the station identifier, the station name, the date, and the precipitation, Tmax and Tmin. What I'm going to do is I'm going to click on this first value, which I can tell is in inches. I'm going to hit Shift, Control, down arrow. And that was a really, really fast way for me to highlight 11,323 rows of data. So do remember that trick. And you can see the last data point is the 12th of the 12th month, 31st day. So that'd be December 31st of 2019. I'm going to use my keys, Control C. I've now copied that data range. Window, let's go back to the tool. If you input the data start date as 89/01/01, then the dates here match up. The data source, Climate Data Online, Portland International Airport. It pulls in automatically the storage capacity that I had in the previous monthly model, but I can override this value, and we'll play around with this in a second. And let's, right here, I'm going to select this cell, right click, paste special values. I've just pasted in all that data. And here's what we know about the 4,000 gallon tank. Over the course of 30 years of actual rainfall, that tank would have been empty 3% of the time, with no adjustments in any demand behavior, right? Let's have a look at it. Here's an example. I don't know if you can see this, but I'm scrolling down and it's taking a few seconds for Excel to catch up with me. There we go. All right, well, what we can see is that 4,000 gallon tank capacity, there's 3% no supply days over the course of over 11,000 days, right? So that's 314 days. And it's not every year, right? This year they would have had no issues. This year they would have had no issues. This year and this year. But, you know, every couple of years, there's a couple of tank empty days. I feel like that family could probably justify to themselves that on these years they would cut back on their demand as they're watching, as they're reacting to the low rainfall in real time. But they could also look at what increasing their storage capacity to 5,000 gallons would give them, as well as it's worth looking on while we're at the daily model at what the 3,000 gallon tank performance is like. With that, I want to show you some of the awesome new improvements to version 2 of the Rainwater Harvesting Daily Tool. Underneath the feasibility summary on the summary page, you'll continue to see the project information, the climate data, and the system design. And then under the supply and demand heading, you'll see the tank volume across the whole data set, the same chart we've just been talking about. The x-axis has been improved. It now shows the years. But below that, there's a couple of new charts. The first one is tank volume year averages. And what we've done here is that we've taken the average tank volume for every single day in the course of the year over those 30 years, and we've plotted on average the volume. So you can really see here that in mid-January, on average, the tank's been full, and in mid-August, on average, the tank is almost empty. So this is really insightful, really great information, and the max and the min range is also shown. The last chart that I'm really excited about is this storage capacity versus no supply days versus reduction in overflow. And there's so much insight that can be gained from this chart that it's worth diving into in a little more detail. Let's zoom in. So what you can see here is on the y-axis, 0 to 100%, and on the x-axis, the tool has actually varied the storage capacity for you and has plotted out the performance of your rainwater harvesting system for different assumed storage capacities. And Peter and I have already talked about how important and insightful this graph is. You'll see the blue line is the days with no supply, the percentage days with no supply, and the red line is the reduction in overflow. So the same nonlinear curve, and you can see you hit a point of diminishing returns. If this particular family had municipal backup and they were just looking to cost optimize and put in minimize the cost of their tank while maximizing their rainwater use, somewhere around 1,000 gallons would probably be a great choice for them. Because they're off-grid and they don't have backup, they're going to probably be looking at selecting a tank size. It really just comes down to budget and what they want to spend. But 4,000 gallon tank in the daily model is also, I think, a really reasonable tank size for that particular family to go with for their off-grid home. This Oregon family might also choose to go with a larger tank size if the cost of backup is really expensive. So there's some very context-specific decisions they need to make, but the chart like this one is really valuable for them to try and wrap their head around what size they should opt for in the tank. And don't forget that although this was a relatively simple example and we didn't need to do a ton of iteration, there could certainly be scenarios where you have to go back and reevaluate the size of your catchment or reevaluate your demands. And that's where those step-by-step process diagrams are particularly useful. So keep those handy and look at those when you are approaching iterating for a solution. Hopefully that lesson gave you some great insight into how to use the monthly model and as well how to use the daily model, some pros and cons, and I hope you play with both and share your insights with us.